Assalamu alaikum everyone. Welcome to another video of Chemistry with Sarab Tasabe. In this video, we're going to look at giant covalent structures. Now let's recall that when we were doing ionic compounds, we studied that all ionic compounds have a giant structure. Similarly, in the last video, we saw covalent compounds, and those category of covalent compounds were simple covalent compounds. But covalent compounds are also giant. Examples of giant covalent compounds can be diamond, graphite, silicon dioxide. These three are in your syllabus. Let's first look at diamond. Before we'll go and study the structure of diamond in detail, we need to see the concept of allotropes. Allotropes are different structural forms of the same element. So when I talk about diamond is made up of only carbon atoms. So all of these black dots are carbon atoms. So diamond is basically carbon, but a different form of carbon. Diamond is a giant covalent structure. Why are we saying it's a giant covalent structure? We can also call this as a lattice. Diamond has a giant covalent lattice, because lattice in this case is regular arrangement of carbon atoms. This is a giant structure because it is a continuous pattern of atoms covalently bonded with each other. And if I look at one carbon atom, this carbon atom, each carbon atom in diamond is covalently bonded to 4 other carbon atoms. 1, 2, 3, 4. So if I have to define the structure of diamond, I would say that diamond is a giant covalent molecule. It's a giant covalent structure. Diamond is not a molecule because it does not have any set number of atoms. Like how many carbons are there, we don't know. So we can't call diamond as a molecule. Diamond is a giant covalent structure in which each carbon atom is covalently bonded to 4 other carbon atoms. So if you see the middle carbon, it's bonded to 4 other carbon atoms, and this is a tetrahedral arrangement. It's like a tetrahedron, like that. It's a tetrahedral arrangement. So to 4 other carbon atoms in a tetrahedral arrangement. So when we are describing the structure of diamond, we also specified that diamond has covalent bonding. It has a giant structure. Each carbon atom is covalently bonded to 4 other carbon atoms, and the arrangement of the atoms is tetrahedral. This is how we define the structure of diamond, right? Now, diamond, since it's a huge structure, it's a giant covalent structure, when we talk about the properties of diamond, we will talk about the properties of all 3 together. But when we look at diamond, since a giant covalent structure, it will have obviously high melting and boiling points. And why it will have high melting and boiling point? Because I have to break these strong covalent bonds in order to melt diamond. So let's look at graphite now. Graphite is also a giant covalent structure. And graphite is also an allotrope of carbon. So these black dots are carbon atoms. But what's different in diamond and graphite? In diamond, each carbon atom was covalently bonded to 4 other carbon atoms. In graphite, each carbon atom here, you can see, is covalently bonded to 1, 2, and 3 carbon atoms. 1, 2, 3. So is also a giant covalent structure in which each carbon atom is covalently bonded. This whole thing is graphite, and it will also have more layers beneath that, loads of layers, in which each carbon atom is covalently bonded to 3 other carbon atoms. Not 4 other carbon atoms, to 3 other carbon atoms in this case. In hexagonal rings hexagon, in hexagonal rings. You see these rings? These are hexagons. 1, 2, 3, 4, 5, 6. 1, 2, 3 in hexagonal rings. In hexagonal rings, and has weak intermolecular forces of attraction. Intermolecular forces of attraction between the layers. If you see graphite, this is one layer or sheet of graphite, this is another layer or sheet of graphite, this is another layer of sheet of graphite, and you see these dotted lines, these are weak intermolecular forces between the layers. Weak intermolecular forces. Now again, graphite is not a molecule, it's a huge structure, but between the layers we have weak intermolecular forces. Let's look at silicon dioxide. Silicon dioxide also has a tetrahedral arrangement, like that. You can see over here. It's a tetrahedron in this case. It's a tetrahedral arrangement. But in silicon dioxide, if you see these black dots are silicon and white dots are oxygen, each silicon atom is covalently bonded to 1, 2, 3, 4 oxygen atoms. And each oxygen atom is covalently bonded to 2 silicon atoms. So silicon dioxide is again a giant covalent structure, in which each silicon atom is covalently bonded to 4 oxygen atoms, and each oxygen atom is covalently bonded to 2 silicon atoms in a tetrahedral arrangement. And this is a continuous pattern of these atoms: silicon dioxide, graphite, and diamond. Diamond and graphite are allotropes of carbon. Silicon dioxide is separate. It does not contain carbon, hence it's not an allotrope of carbon. So, for example, I can write examples here: diamond and graphite. Diamond and graphite. In the next video, we are going to see the properties of giant covalent structures with reference to their structures. And we will also see what are the uses of diamond and graphite in real life. Till then, stay tuned everyone.